thank you all for coming. Today you get a dual header. You get two presenters for the price of one. And Robert and I are going to speak about the various capabilities that we have, new capabilities that we have in the Earth Lab, as well as in the WIGL. And before I hand over to Robert and introduce Robert, there is a much bigger team behind this presentation. And so whilst we're up here presenting, there is a much bigger team that has first built a foundation for geochemistry in the school, but has also been instrumental in helping to set up and advising on many of the different aspects that you'll see this evening. Okay, so, of course, Alan Wilson, Marlon, Sarah, who is a postdoc here pioneering the remote SIMS facility, but also helping with the mineral separation, and of course Joe, who's been a foundation behind keeping a lab functional and operational, Linda, who has done much of the work that you'll see in the isotope section, and myself and Robert. So I'm going to hand over to Robert now, but first let me introduce him to you. He is born in Slovenia. Thank you. I was going to say
how come you can't remember?
Slovenia. Too many S's. Born in Slovenia, and he was educated in Germany as well as Australia, and did a postdoc in New Zealand, and worked in industry in Australia for a significant amount of time before coming here to join us in Johannesburg several years ago. So Robert, I'm going to hand over to you to talk about laser ablation capabilities at Wits. It will be. It will be available on YouTube tomorrow morning.
Fantastic. Thank you, Grant, for the introduction. So my part of the presentation today is really to give you an update on the newly established laser ICP-MS facility here at Wits. And of course I'm going to talk about the instruments we have, but I'm also going to talk about the methods that we have implemented so far, including data reduction and workflows. And I will talk about performance. I want to demonstrate to you that we can do certain things already, and I'll back that up with reference to reference materials. And finally, I want to inspire you to use our lab by highlighting some of the novel applications that have recently emerged in the field of laser ICP-MS. So the three instruments basically combine to form the laser ICP-MS system. Firstly, we have the little ICAP, quadrupole ICP-MS. It's currently doing routine solution work, but we're planning to connect it to the laser at some point. Then we have the bigger brother, the Thermo Fisher Element sector field instrument that is currently working in along with the laser. And finally, the laser itself, which is an Australian scientific resolution excimer laser. The same is currently operating at UJ as well, and I think an instrument was recently installed at UCT. The instruments are run by 3 computers that sit on a desk adjacent to the instruments, and the data reduction, data visualization is done separately on 2 computers in the lab as well. And in addition to that, we have an old existing new wave UP laser that we're planning to use for various things like sulfide work or laser cutting. So I'd like to start off with some general information on laser ablation. What is it used for? It's used to determine chemical and isotopic compositions of solid and semi-solid materials. So these materials include rocks, minerals of course, glasses, speleotherms, melt inclusions, stone artifacts, but more. Also we can include organic materials, for instance bones, teeth, shells, corals, ice, even soft tissue. For instance, I know at Melbourne Uni, where there is a great team of laser ICP-MS people, they're experimenting with brain tissue of rats using laser ICP-MS technology. So the idea here is that a finely focused laser beam interacts with solid material and it ablates, it dislodges the material, it ablates it and forms an aerosol which is then swept through a mix of gases into the ICP-MS plasma source. And it's a spatially resolved technique, so we can actually see what we are lasering, okay? And this environment can be either a CL image or a thin section. The instruments are very sensitive, so they can detect metals down to PPT levels, and importantly, we can couple compositions and isotopes in one go. So the laser we use is, as I said, the ASI resolution SE. At the heart of this laser system is the laser itself. It's a small box sitting at the bottom of the body. And the idea behind this is that we have a mix of gases, a halogen gas, usually argon, and a reactive noble gas and a reactive halogen gas that can form a very unstable compound called excited dimer. The short version of that is excimer. And it can emit light of a specific wavelength, in our case 193 nanometers. The spot size are quite variable, can go from 2 to 80 microns, and in different shapes, so they can be round, square, or even rectangular. The fluence of our laser ranges from 3 to 20 joule per square centimeter. Fluence is basically the energy density delivered to that material. Lasers have evolved with time, so the early lasers were solid-state lasers. They operated at relatively high wavelength and at relatively low energy per photons. And with time, these lasers evolved to excimer lasers, which operate at quite low laser wavelength and very high energy per photon units. And why is that important? So minerals tend to absorb some of the laser, but they can also transmit some of the laser beam. And this is a function of wavelength, as you can see here. Okay? So the lower wavelength lasers have a tendency to be transmitted less. In other words, the ablation is more efficient. Secondly, the lower or the higher wavelength lasers fractionate the signal more severely, which is not desirable. And thirdly, the older style lasers generated laser pits that were quite ugly looking. You can see here that the pits are fairly irregular, and that also impacts on the laser signal and the laser stability. And to the right you see here a ablation pit generated by the excimer 193 nanometer laser. After 100 pulses, we can see that the laser pit has a very even bottom, and is pretty well defined with very nice, clear, sharp edges. And this basically means that the ablation performance is greatly enhanced. The samples sit in what is called an ablation cell. There's various designs on the market, but we use the Lorraine Technic ablation cell, and it's got a unique design. So in this cell, we can optimize the gas flow conditions to make sure that we have a stable and good signal. And we use this by a variety of gases. We use helium and argon, and we also use nitrogen to enhance the signal stability and sensitivity. We can take a number of different sample types into our ablation cell. So we can use, for instance, up to 20 mounts in one sample holder. We can even put entire rocks or bones or whatever into the ablation cell. The sample stage is very precise. In other words, the movement of the cell is extremely precise, and it's a so-called dual volume cell. So we have a larger cell that includes a sample stage, and inside sits a small volume cup just above the sample. And what this does is it ensures that the gas flow dynamics within the cell are stable and uniform. This in turn reduces fractionation and enhances the signal. So currently our laser is coupled to a high resolution sector field ICP-MS. And just briefly, this instrument consists of a sample introduction part. In solution mode, the sample gets introduced to a nebulizer into the spray chamber, where it then enters or gets aspirated into the ion generation unit. So inside the torch is a plasma that ionizes the material. The ions are then sucked in through two cones into an area where we have a variety of lenses and a quadrupole to manipulate the ion beam, which then travels into the magnet where the ions are being separated. I will talk about that in a minute. Finally, they enter the electrostatic analyzer to eventually make it into the ion detection unit. So very briefly, as I said, the sector field consists of two analyzers, a magnetic and electric sector analyzer, and this is shown here. So here is the magnet. The ions are separated according to mass and charge. And then they fly into the electrostatic analyzer where they are actually filtered according to the kinetic energy. Finally, they make it through a slit into the detection unit, and this slit basically enables us to resolve isobaric interferences. And what that means is that sometimes we have species that have basically the same mass, so the mass spectrometer doesn't really know how to separate these, okay? And with the aid of the slit, we can resolve these different species that basically have almost the same mass. The instrument is very sensitive. Just to put numbers to it, 1 ppb of an intermediate mass translates into up to 1 million counts per second, which is very high resolution. And this is very important because it basically means that we don't need much material. This becomes important when we ablate individual minerals and we want to ablate individual domains, small domains inside that mineral. Our instrument is equipped with a Faraday cup which enhances the dynamic range. In other words, we can measure anything from down to ppt up to weight %. And finally, through the combination of magnet and ESA, we have a situation where the instrument can scan very quickly over the entire mass range. So one sweep over the entire mass range takes 1/3 of a second. Okay, just very briefly, every instrument or every technique has pros and cons. And this is a table pulled out from Schalteg et al. And showing three different techniques: ID-TIMS, SIMS, and laser ICP-MS. And the ID-TIMS is, of course, by far the most precise, but it's very time-consuming and very costly, and not many labs can afford to do that. SIMS and laser ICP-MS are very comparable in many aspects. For instance, if you look here at the absolute H resolution for SIMS and laser ICP-MS, it's virtually the same. Okay? So it's a myth that SIMS is always the more precise technique. There's various other aspects that people want to consider when choosing SIMS versus laser ICP-MS. So for instance, the SIMS is a great instrument to have, but it's very costly. And it requires a very highly specialized operator, which is in contrast to a laser ICP-MS, which is a very low-cost equipment, and a user can be trained within a few days. The SIMS is time-consuming. So for instance, one single uranium lead analysis takes up to 15 minutes. Laser ICP-MS does the same thing in 1 minute. The big strength of the SIMS is, of course, it's virtually non-destructive, whereas the laser ICP-MS drills visible holes into your mineral. But what we can do with the laser ICP-MS is we can couple isotopes with compositions. Okay, so we can couple H and composition. Very quickly, what's the workflow in preparation for laser ICP-MS? Obviously, we need to crush the rock. We can do that with a self-frac or with a conventional jaw crusher. We extract the heavy minerals either using Wilfley table or heavy liquids, and then we need to do magnetic separation, for instance, to separate zircon, which is a non-magnetic mineral, from magnetic minerals. This is being done by friends, magnetic separator. Finally, we pick the minerals under microscope to then get them mounted or embedded into an epoxy. Generally speaking, we can mount up to 500 grains into one mount. Okay, so that's what they look like, and then we need to do CL imaging. The reason for that is we need to expose the interior of minerals to basically define targets. You can appreciate from this image that zircons crystallize during different events. So you want to date a particular event, you need to find the right target. Then we need to digitize the points, and that is done with the laser ICP-MS software. And if we do trace metal analysis, we need to add an additional step, which is we need to measure a weight, major element such as calcium by the electron microprobe to use it as an internal standard for the laser ICP-MS. Our software with the laser ICP-MS is quite user-friendly and intuitive, and it's very easy to build a sequence of points. So this is the sequence, here are the points, and we can define either single points, we can define lines, we can define areas, or even very complex patterns can be ablated. So this is a conceptual workflow for uranium-lead zircon dating. We need to define targets using CL, and here it becomes important what we want to research. Are we interested in magmatic processes, metamorphic processes, or are we interested in detrital work? We then measure by ICP-MS, we then do data reduction, and we need to validate. Validation goes through several steps. Firstly, we need to check if we actually lasered the right spot. Okay? For instance, if we haven't, we may end up with mixed ages. We need to check that we didn't laser into cracks because they often contain common lead, and we need to exclude inclusions. Quite often we find that the zircons will give us age populations, and then we need to assign ages to geological events. Very briefly, the uranium-lead zircon technique is very powerful simply because we have got two decay schemes, and they allow us to check the internal consistency between these ages. Okay, so if these two ages coincide or match, the data points will plot on this banana-shaped curve, which is the concordia. But quite often we see that zircon grains or data points do not plot on this concordia curve. They plot away, and in this case they're called discordant. Okay? And there's two major mechanisms that can cause discordance. One is lead loss. So imagine we have a zircon that crystallizes at time true. It then suffers lead loss, and the data point moves upward. And what we then measure is essentially three different ages. Okay? None of these three ages is actually the true age. The other process that can cause discordance is common lead. Common lead means it's lead that is not produced by radioactive decay. And if that happens, then, for instance, in this case, a zircon crystallizes at T true, incorporates common lead, and this data point gets moved away from the concordia as well. So these are 2 points to keep in mind when doing uranium-lead zircon geochronology. Luckily, we use a software package that is inbuilt into our data reduction software called Visual H, which allows for common lead correction using the method by Tom Anderson. Okay, quickly, data reduction. Data reduction is very important. Oh, I see. We use Iolite for this. Iolite was developed in 2008 by people at the University of Melbourne, and it's nowadays widely used. And it basically goes or proceeds through various logical steps, including data import, baseline correction, and then we define the calibration standards, the samples. We do instrument drift correction, and importantly, the software is very flexible in terms of defining laser-induced downhole fractionation corrections. And finally, we can choose a particular DRS, data reduction scheme, within this software to crunch a particular problem. Why do we use Iolite, and why do I personally like Iolite? It's compatible with most instruments. It can graphically display very large data sets as raw data. It's compatible with Windows and Mac. It allows you to visually examine quite a number of isotopes, and it can be applied to isotopic measurements or compositional measurements and so forth. And maybe most importantly, it's an open code software, so people can actually add software applications into this existing software, and they call it add-ons. Laser ICP-MS depends very heavily on good quality standards, and a good quality standard is a standard that is homogeneous and doesn't contain common lead. Secondly, laser ICP-MS needs to use matrix matched standards. In other words, if we want to measure zircon, we need to use a zircon standard. if we want to measure calcite, we need to measure a calcite standard. I can proudly say that we now have built a very comprehensive collection of standard materials, including various minerals, but also glasses. Glasses are being used for trace metal work. So you now you now probably wonder, can they actually deliver? Can they meet the key performance indicator, namely reproduce certified reference materials? And I will demonstrate that to you right now. So we have analyzed two of the most widely used reference materials. One is BHVO and one is BIR. And what I have done here is I have plotted the measured concentrations against the reference values for over 40 elements over a pretty wide range of concentrations. And you can clearly see, it's fairly self-evident, that they define a very good, strongly correlated trend, which basically means we can reproduce the reference values. There is a bit of deterioration of this trend down here, but remember that we're looking here at 0.1, below 0.1 ppm trace metal concentration. To the right are chondrite normalized rare earth element plots of measured and reference values for BHVO and BIR. And again, you see there's a very good correspondence between reference values and measured values. Okay, now let's turn to zircon standards, the second major application in our lab that we have successfully implemented. So one of the most widely used reference standard is Plesovice, and these are actually data produced in our lab in two different separate runs, and you can see that the data cluster along the Concordia, and they produce ages of 337.5, you can't read that, and here 339 plus minus 0.9. If you have a look here, I highlighted the reference or certified value for this particular standard, and you see that the reference value for this particular standard is 337. In other words, we reproduce this particular standard extremely well. If we now look at two other standards, 91500 and Temora, we can see that our lab produces an age of 1,063 plus minus 3.5. Compare that to the certified reference value of 1,065, and you see we can reproduce that age also very well. And finally, Temora, the youngest of these four, the second youngest of these 400 at 421 plus minus 1.5, and it is just slightly off from the reference value at 417. Finally, a standard, an in-house standard that could be of great interest to many of you. I obtained some zircons from Ellen from the Bushveld complex, zircons from samples JGL and PGMT. And these zircons were previously very exactly dated by Ellen and Amin Se using ID TIMS at 2055 in both cases. And we ran these zircons in our lab. We produced an age of 2048 plus minus 6 and 2053 plus minus 12. So again, excellent to very good agreement between what we produce in our lab and what people have done using ID TIMS. Okay, so I want to now enter the third part of my talk. I want to give you some examples of what I think is novel applications, emerging applications within the field of laser ICP-MS. The first deals with magmatic minerals. So it has long been known that magmatic or zoning in magmatic minerals reflects changes in magmatic environments, both physical and chemical. And much of this information in the past has been retrieved from petrography and major elements. And when you look to the left, you will see there's a series of images. Up here is a petrographic image of a magmatic CPX, and you can see a faint hint of textural zoning. The images below were obtained by laser ICP-MS at Trinity College for various trace metals. In this particular case, they measured chromium and nickel because they're compatible elements. They can reflect mafic recharge, and essentially these images can be generated for all sorts of trace metals. To the right, you see a conceptual sketch of a plumbing system, and compositional types for each of these investigated minerals can be assigned to compositional types in this plumbing system. Okay? So the compositions can either be influenced by mafic recharge, mixing, fractionation, or maybe crustal assimilation. The interesting point here is that these images take anywhere between 1 and 3 hours to make, including experimental setup and data reduction. They are virtually non-destructive, so only 1 micron of the material is ablated, and the resolution is very good. Apparently, these images can show features that are smaller than the laser beam size itself. Okay, mineral imaging can be extended to geochronology. There's a recent paper here by David Chu and co-workers, and as you know, zircons have the ability to preserve many different events that usually shows up in a core rim texture in CL imagery. And the colored images are basically, again, images generated by laser ICP-MS. Here you see uranium, thorium, the thorium-uranium ratio, and ages. And essentially you can map out a zircon in terms of its age. How great is that? Each of these maps takes 10 minutes. So this is faster than SIMS for one spot. Individual ages can then be plotted in the conventional Concordia diagram, and the individual ages can be contoured for density distribution. And what you see here is that this technique resolves 2 major age groups, and in between you have a Discordia mixing line. An interesting application, or especially for me I think, is the absolute dating of carbonates. As you know, carbonates can form in many different environments. They can form as sediments, as precipitates, they can form through hydrothermal activity, but they can also form along fault zones during deformation. And 2 examples are given here. This paper just came out in Geology, and there's another paper that is a bit older, where people actually looked at carbonates that formed silicon-side fibers, and the carbonates were dated. And in this case, for instance, they were able to assign different ages to orogenic events and extension in a continental setting. And in this case, absolute carbon dating was used to study the opening of the Atlantic Ocean. How good is that? So carbonate dating requires elemental imagery. Why? We need to, when we do laser ICP-MS, we need to target domains with high uranium lead ratios and low uranium lead ratios in order to get an isochrone which has a sufficient spread so the age is sufficiently precise. But interestingly, also by combining textual observations with ages and let's say stable isotopes and rare earth elements, it's possible to infer, for instance, the sources of the fluids that precipitated these carbonates, or the temperatures or even the crustal depth. Okay, the second final slide is the last, I think, emerging application. Laser ICP-MS referred to as petrochronology. Some people call it zircon chronochemistry, whatever pleases. Petrochronology is the concept or approach of combining age information with compositional information, and an example is shown here, where people have plotted ages and color-coded them according to their compositions. A prime candidate for petrochronology is zircon. A beautiful specimen is shown here. And zircon has often a very complex and intriguing internal stratigraphy, showing up as, for instance, cores and rims, and there's various generations of rims, as you can see here, and there's various types of zoning. So this is magmatic zoning, and then here you've got this convoluted zoning, and each of these domains can be dated individually, okay? And each domain can then also be measured for various compositional parameters, such as thorium uranium, which is, for instance, a fingerprint for magmatic versus metamorphic. Rare earth elements can be measured, and they can tell us something about mineral fractionations, such as garnet or changing magma compositions with time. We can measure with laser ICP mass titanium, not only in zircon, but in a number of other minerals. And titanium can be applied as thermometer, so we can basically link composition with temperature and time. And finally, by adding stable isotopes and radiogenic isotopes, we can fingerprint mantle and crustal sources, or we can identify juvenile melt formation versus reworking of particular rock. Okay, I want to finish off with a little vision statement. Our vision, long, medium, and long, short, medium, and long term, is to produce reliable, high-quality data. How do we achieve that? We want to implement best practice, for instance, use the right standards, or use very good data reduction approaches. Okay? We believe that we have the best instruments to do this job. We will aim for fast turnaround. Okay? Obviously, this depends on various factors. It depends how many users will be trained, to what level. It depends if at some point we can raise funds to employ a dedicated instrument scientist. And it depends on the demand and the range of methods we are trying to implement. We want to set up novel methods to drive innovative research at WITS. And we, of course, want to train a new generation of researchers. We want to train students, we want to train postdocs, we even want to train researchers that come to visit us or are in-house. And finally, we want to continue to provide good analytical service to our school, to student projects, and also to the industry. Thank you.
Okay, thank you, Rob. So now we're going to take a turn and talk about the WIGL, the WITS Isotope Geoscience Lab. And I'm going to talk to you about what the capabilities are and how we've progressed since the opening last year in March, February or March. The first question you may be asking is, why solution? Rob's demonstrated some great applications of laser data. Why in the world would you ever want to do solution work again, and why would you ever want to do isotopic solution work, for instance? If we can produce all of this in situ, what's the role for solution? And the main idea in my mind is that with solution work, you first of all get better precision, we can separate the elements of interest, and it also allows us to do multiple isotopes on one aliquot of material. So laser ablation, whilst it's spatially controlled, doesn't have the ability generally to do multiple isotope systems from one aliquot of rock. Of course, it's also very difficult in laser work to be able to get enough analyte from a laser material into the laser. And so for elements like neodymium and hafnium, you just can't ablate enough material from that rock to get into the mass spectrometer. Okay, so this is the WIGL, as we refer to it, and most of you have seen it. If you haven't, you can go and visit it in the lower ground floor of the building. And why the WIGL? All right, why did we build the WIGL? And the main thing was to be able to separate elements of interest from a variety of different kinds of matrices for precision isotope ratio measurement. And that's really important. That separation is important because if you try to do that just on a whole rock powder, you wouldn't get the same kind of resolution and accuracy than if you separate the elements of the isotopes that you want to measure. And of course, I have to mention that these capabilities are built on a really strong foundation of geochemistry in the school. And so here you can see Hugh Alsop working on a TIMS, the only TIMS left in Africa, which you can see in the museum. And there were pioneers of geochemistry working in the school in the 1950s and 60s, developing things like the isochron. So Nicolason developed the isochron, and Alsop and Nicolason were some of the first geoscientists to measure rubidium strontium ages of rocks from South Africa. And so we're building on a strong background, and that I think is very inspiring, certainly for me. The other thing that you have to do if you want to separate elements and measure isotopic ratios is make sure that you have a very, very low background element concentration. If you're interested in lead, for instance, and lead is a very difficult element to get out of the environment, and you don't have a clean lab, you're never sure whether you're measuring lead from your sample, from your zircon, for instance, or lead from the environment. And so we need really ultra-clean, non-metallic facilities with low background or blank concentrations. And that's what the WIGL is. So you can see this from the window of the WIGL. That's where we do the actual element separation. What do we mean by clean? You know, how clean is clean? And so the first very important thing is air quality. We want to control the air quality. And for those of you that hear the buzz in the background when you walk through the building, that is the air system cleaning the air for the WIGL. And so the room air that you're breathing right now has 1 million particles per cubic foot that are 0.5 microns in diameter. Okay? And so that's the air that you're breathing right now. The cleanest, well, the general air in the WIGL is about 1,000 particles per cubic foot. And in the cleanest hoods, we've recently had a certification that puts us between 1 and 10 particles per cubic foot. So we've reduced the particulate count in the air dramatically, and it's a great place to work if you have allergies, because all of those materials are now removed from the air. That's why Linda's so healthy. She breathes that air all day. Okay. And that you can see is a plan of the laboratory. There's various rooms going from the entrance over here into a basic cleaning room, a sample digestion room, and then the cleanest room where the cleanest air enters, which is where we do all the column separation, all the separation of the elements. Of course, we also want to protect the lab from ourselves because we shed particles all the time. And so it's a full suited up lab, gloves, full suits, no jewelry, no metal teeth, those kinds of things. And here you can see two researchers from UJ, Tebogo Makubele, who's a lecturer at UJ, and his student Sibusiso, who are developing aluminium and beryllium isotopic separations, which I'll talk about in a second. Okay, we also have to make sure that everything we use in the lab is really clean as well. So all the reagents that we use to dissolve the rock, which is a fundamental aspect in this process, have to be cleaned. And so we take what we consider dirty reagents, which are ppm level metal abundances, and distill them once or twice. It's never triple distilled like whiskey, but normally double distillation gets rid of all the metals that we want to get rid of. And then, of course, we also have to clean the water. All right, and so we have water which is the cleanest water you can get with almost no ions in it, which you can't drink, by the way. All right, so that's all very wonderful to say we've built this lab that has such low blank concentrations, but can we quantify that? And so what you see here is a measurement that was done by Alan and Marlon in the Earth Lab a few days ago, measuring the blank levels. And the first part of this graph over here is measuring the blank levels in water in the lab and HCl, nitric acid, and HF, all the reagents that we use in the lab. And you can see that the blank levels on this logarithmic scale for most elements are less than about 100 picograms, okay, for all the reagents. What's more important, what I really want to emphasize, is what the total procedural blank looks like, okay? And of course, this is not for all the elements, but for separating strontium, for strontium isotope ratio measurements, and for separating neodymium, you can see the blank levels there. Strontium less than about 60 picograms, rubidium less than 10 picograms, neodymium less than 5 picograms, and samarium less than 1 picogram. And just as a way of comparing, because these numbers may not mean very much to you, these lines here represent blanks that I was exposed to at Carnegie, and so we are producing, in my mind, very, very good blank levels with most of the elements lower than the blanks at Carnegie, which is a very well-established isotope lab. And these are total procedural blanks, so from digesting the rock all the way to having it dry down in a beaker, ready for the mass spectrometer. So what is the procedure? Rob demonstrated the procedure for preparing for laser ablation work. What is the procedure here? And we obviously start with a rock, or a fossil, or an artifact of some kind. And generally what we want to do is to create a powder from that, or to drill out some powder. And we then want to weigh that powder very accurately. And this is a scale in the WIGL, which measures down to 1 microgram precision. I would not like any updates. And then we want to dissolve that weighed out material. Okay, and so there's various ways of dissolution. Here you see beakers dissolving quartz for beryllium aluminium measurements in a very clean hood on a hot plate. But we can also digest very refractory material using a microwave digester. And then we do the column chemistry, and I'll show you some examples of the kind of column chemistry that we do. And we do the column chemistry to be able to separate different elements. So a normal solution ICP-MS measurement where you're looking for the entire trace element suite, you don't do any element separation. But here we're looking for ultimate precision for one particular element, and so we want to separate, for instance, strontium from calcium or from rubidium, because there's interferences between those elements. And so we have set up, and that's really the hallmark of an isotope lab, is setting up the column chemistry which separates out these elements so we can get high precision and avoid any interferences in the mass spectrometer. And once you've separated those elements, you then take it to a mass spectrometer facility. And in general, these mass spectrometers are magnetic field or sector field instruments like what we have in the Earth Lab, which Rob has described. And they, of course, are ICP instruments, so they ionize the sample using a plasma. But what is different about the mass spectrometers that we use for isotope ratio solution measurement is that you have multiple collectors. And so the element instrument we have here has one collector and a magnet and an ESA, but these are referred to as multi-collectors. So you can measure different isotopes of an element at once and then create a ratio. And that makes a much more stable and precise measurement. A hallmark of isotope geochemistry as well is isotope dilution. And I put this here because it's important to understand what it means and why you would need it for your rocks. And so really what it is adding a spike, which is an artificially enriched material with a non-natural isotope composition, okay, into your sample, and obviously weighing it out very precisely. And the best kind of analogy to draw here is fish in a pond. Okay, so I don't want you to count how many fish are there because I can't trust whether you can count correctly. Okay, but there's another way of working out the number of fish in that pond without counting them all, without having any kind of standard, and with only sampling a small population of the fish. So we have a natural sample of fish, but if I add a spike, which is what isotope dilution is, adding a non-natural composition into a rock, and in this case we're going to add a blue fish, which is non-natural, into that pond, and we're going to add 5 blue fish into that pond, and then we're going to measure, analyze, and work out the ratio of red or black fish to blue fish in a subsection of the population. Okay, and so if you count and you create a ratio of the black fish to the blue fish here, you'll see it is 10 to 1. Remember, we added 5 fish in the beginning. And so really what isotope dilution does is uses an isotopic ratio and the amount of an enriched material added to calculate a concentration. So we know that there are 50 fish in this pond using this isotope dilution calculation. And so why is it important for geology? Well, it allows you to very precisely and accurately determine parent-daughter concentrations and parent-daughter ratios, and that therefore allows back calculation and precise initial isotope ratio determination. And that's crucial for any rock that's older than 50 million years old, right? Because you have to back calculate your ratio in time, and you aren't able to do that for rocks, or aren't able to do it accurately for rocks older than 50 million years if you don't have a precise parent-daughter ratio. So I mentioned earlier the mass spectrometer that's involved. It's a multi-collector ICP-MS, and this is where a very important isotopic collaboration is formed, because for one university to be able to try and get the mass spectrometer and the clean lab would be a very, very expensive and probably unsuccessful endeavor. So we have built the clean lab, and we are collaborating with colleagues at UJ who a year or two ago bought a multi-collector sector field ICP-MS. Theirs is, of course, coupled to a laser as well, but it can also do solution work. And so all the chemical separations done in the WIGL can be analyzed on this multi-collector at UJ. And I'll talk about prices, etc. later on. Of course, if, for instance, you were interested in doing TIMS analyses, thermal ionization mass spectrometry, and you had a colleague in a lab, you would be able to do the chemistry here and then send the samples to that lab. So let's look very briefly at the elements and isotopes of interest. Circled in green here are the calibrations that have already been done in the WIGL. So we've already calibrated the chemistry for rubidium, strontium, lutetium and hafnium, samarium and neodymium, and for silicates we've already calibrated iron, copper and zinc isotopes. And unfortunately there's not time to go into all the different applications for these isotopes. You'll be familiar with the radiogenics like strontium, neodymium and hafnium for isochron age dating and for tracing geological processes. Iron, copper, zinc, as you can imagine, are very useful for looking at oxygen fugacity and changes in source of particularly sulfides, but also silicate lithologies associated with ore deposits. The column calibration is in preparation for beryllium and aluminium, which are cosmogenic isotopes, so we can use that for dating erosive processes, and that's being set up by Tiboko at UJ. We are also setting up calcium coupled with strontium and iron, as well as copper and zinc, mainly for paleontological applications, because these different isotope systems reveal a lot about paleo diet and paleo range. And in time, we'll also, of course, set up lead and uranium and thorium separations. And so to demonstrate what these separations look like, this is the legendary work of Linda, and it really is legendary because it takes a very long time to do and a great deal of patience. You can see measuring a column chemistry set up in 1 milliliter increments takes time and incredible patience. So what you see here is the separation for rubidium, strontium, samarium, neodymium, and lutetium, hafnium. And we do that in 3 stages. But the important thing is we can get that from 1 aliquot of rock, from 150 to 100 milligram weight of powder. We can determine and separate strontium, rubidium, samarium, neodymium, lutetium, hafnium. And so we do 3 stages. The first stage separates out a variety of elements, rubidium, strontium, samarium, neodymium, and it separates those elements from lutetium and from hafnium. And so here you're seeing intensities over the column elution. And so we've separated a bunch of elements, and we've got a pure lutetium fraction and a pure hafnium fraction. We then take this fraction over here and want to separate rubidium and strontium from samarium, neodymium. And so here you can see the separation of rubidium from that dissolved rock, and it's separated very nicely from strontium. And that, for instance, would avoid any interferences between rubidium and strontium, which in the mass spectrometer have similar masses. And then we take the next fraction, or the matrix from there, and separate neodymium from samarium, once again avoiding fractionations caused by those elements. And that process takes from digestion to final separation and dry down approximately 5 days. Linda, would you agree? 5, 6 days? 7 days? 3 days of chemistry and about 3 days of digestion of the rock. Then this is the heroic work of Loic Lebras, a PhD student here, who has essentially calibrated the copper, iron, and zinc separation curves. You can see copper being separated from iron, being separated from zinc, which can then be dried down and measured on a mass spectrometer. And this is the separation of beryllium. Okay, so what is the status right now? In fact, last week we were testing the ratios produced from this column separation on the multi-collector ICP-MS at UJ. That step is complete, and we are in the progress of reducing the data, and we'll start the ratio testing for calcium, strontium, iron, copper, zinc separation, which is good for sulfides and oxides as well as for fossils, in June. we also learned some exciting news today, courtesy of Marlena and Henriette at UJ. And this is a bit of reference material testing for neodymium isotopes. So JNDI is a standard neodymium isotope, or a standard for neodymium isotopes. And for the JNDI standard, in the WIGL, processed in the WIGL, we get an isotope ratio, 143, 144 neodymium isotope ratio of 0.52085 with precision in the 6th decimal place, which is what you want. And the reference value for that JNDI that was obtained when the mass spectrometer was installed was 0.512090. So we are very, very close to producing a spot-on value for that lab. And this is just after 1 day of testing. So we're quite proud of that, and I think it'll just get better with time. So we also plan to implement some future testing, the first being lithium isotopes. That'll be pioneered by Marlena and one of her students at UJ. And I think that there will be a lot of demand for rhenium osmium isotopes as well. And we've already got some access to spikes from Carnegie for rhenium osmium, and we'll start setting up that in the near future as well. And just to illustrate, I thought this was a nice way to end, because often people think of laser ablation work and solution work as being completely separate. But what we're beginning to try and develop here at Wits is a way of combining the power of solution work with the spatial resolution of laser ablation work. And so what we're doing with the laser, and this is really being pioneered by Andrew, a PhD student here in Loic, is to use the laser on a thin section to cut out material, so spatially controlled sampling. And here you can see an example of plagioclase being cut out of a thin section in secondary electron imaging. There is the actual piece of plagioclase being cut out, and what we would then be able to do is to take that piece of plagioclase or any other mineral or fossil, for instance, and then pass it through the solution chemistry, and that allows you to do the multiple isotope systems at high precision using isotope dilution. And to give you an example of that, Andrew did a test on trying to be able to cut out zoning, for instance, in a plagioclase crystal. So this is not actual real zoning, but he was trying to be able to cut out actual zones, compositional zones within a mineral. And he was able to successfully extract that material from a thin section. And then it could be dissolved and processed further. We also, of course, are testing some novel techniques. One is Priyanka testing calcium, strontium isotopes in fossils, and Loic, which is going to develop methodologies for iron, copper, zinc in sulfides and oxides. Of course, you probably want to know about costs, both for the laser ablation system that Robert's talked about, as well as for the WIGL, and the costs for the mass spectrometry on solution work at UJ. And so you can see for laser ICP-MS, for uranium, lead, or trace elements in situ in the Earth Lab internally, we'll charge 2,200 Rand per day. Okay, and it varies how many points you can do per day, and Rob can probably advise better on the number of spots, but certainly for the trace element work we've been testing, you are able in a day with setup and even data reduction to do around about 80 to 100 spots for trace elements. The WIGL separation is still in its provisional stages, but we envisage that for certainly the radiogenics, strontium, neodymium, hafnium, we're looking at 2,000 to 3,000 Rand for 8 samples. So to process those samples, 8 samples, it'll be between 2,000 and 3,000 Rand. And then the solution ICP-MS measurements, both for UJ staff and Wits Chimera users on the UJ mass spec, is 2,600 Rand per day. And in a day, you can process approximately 16 solution analyses. So for instance, you had 8 samples that you'd process through the WIGL. On one day, you'd be able to do both the rubidium isotopic measurements as well as the strontium isotopic measurements for 16 samples. Okay? So if you had 16 samples, for instance, processed through the WIGL, you'd be able to do all of those isotope ratio measurements, both the parent and the daughter, in 3 days under the most ideal conditions. Of course, you all know that there is a booking form to access the Earth Lab, and there will be a similar booking form for the WIGL coming up. And it's a very simple process of entering your details and selecting the analyses that you want. It's either per sample in the case of solution work or per day in the case of laser ablation work. And I think the form is fairly self-explanatory. So to end off, both Robin and I must pay tribute to many people that have helped in developing this. This is not something that two people can do alone. And of course, funding from the National Research Foundation is crucial to this, as well as from Chimera. Wits University contributed a huge amount to the Isotope Lab. And I must also mention that Polymatrix, the company that built the lab, is a South African company. And I feel quite strongly that we have built a world-class laboratory through a South African company, which I think is very important. And of course, there are many other people, including Grant Cawthorne, Roland Maas, Dirk Fry, Roger Gibson, Marlene, Henriette, and many, many others, including many of you in the room. So thank you, and hopefully we can do some good science in the future. So, do we have any questions for Robert or myself? Alan.
Robert, one of the things that you didn't mention, and that's within our capabilities, is that there's a field of looking at not inclusions in zircons. People probably are not aware of this, but this is a tremendously rapidly growing field because zircons are so impervious that they encapsulate and melt in any crystallizing system, and we now have them to analyze what that melt is doing inside zircons. We're doing that in Frankfurt, zircon, Bushveld, zircons, and things like that.
Good. You had a question?
Yeah, I just wanted to know for isotope dilution, how do you know how much spike to add?
Oh, that's a really good question. And so you determine that based on the amount of element in your rock. So you have to know broadly, you can also guess, but then you can make mistakes. But if you know, for instance, the neodymium concentration or the rubidium or the strontium concentration in your rock, you can calculate the correct proportion of the spike to add. And it's really a balancing act based on the spike's isotope ratio and the sample's natural isotope ratio. And so you're looking for a certain factor difference between the sample's concentration and the spike's concentration. Very good question. So it does help to have at least some idea of the trace element content of the rock. That's especially for hafnium, strontium, and neodymium. Oh.
Both the UJ and the Wits mass spectrometers, one's multi-collector at UJ, single collector Wits, both have lasers. What's the sort of trade-offs, advantages, disadvantages between the laser equipment here at Wits and laser equipment at UJ?
Okay, so our element is a single collector instrument. It's got a magnet like the multi-collector, but because it's got a single collector, it has got advantages and disadvantages when compared to the multi-collector. So the advantage, I guess, is that because it's a single collector, it has a wide dynamic range. So we can analyze elements at PPT levels up to almost 20%. And the detector can copy that. The second advantage is that because it's only one detector, you don't have to calibrate between 7 detectors. With a multi-collector, you have, let's say, Faraday cups, ion counters, Delhi, maybe, and they all have to be calibrated against each other. For isotope work, generally speaking, multi-collector will always be superior. Why? As Grant mentioned, we've got multiple detectors and they measure simultaneously. With a single collector, it's sequential. So therefore, for multi-collector will always be much better suited for real isotope work. But let's say for uranium net dating work, because we measure so many zircons, for instance, you have a lot of data, and then when you let's say calculate an average, due to the large amount of data points, you still can get a very precise average. But probably the other advantage of a single collector that we can do isotopes, let's say for uranium black, but we can also do trace metals. So which the multi-collector can probably not do very easily. Okay. So these are probably the main differences, and every instrument has got pros and cons. And it would be foolish for us to say we want multi-collector as well, because then there would be two multi-collectors, but no single collector. So here we are, we have a multi-collector in future and a single collector.
Right.
Yeah, thanks, Guy. Really great job. Just question about this. You show that what you can do now with the zircons.
Yeah.
So can we do now something really with patch, CPX, silicate minerals, or not yet?
Yes, we can.
We can.
Yeah, we can. In theory, we can. So the trace metal work in general is a bit more easy. Why? Because we basically use glasses as calibration standards, and the data reduction is easier. The only thing is we need to measure, let's say, calcium or whatever in your pleasure class on the probe, because we then have to use a particular element to then correct on our instrument for instrument drift. So we need to have an independent internal standard value. So that's the only prerequisite for basically mapping out pleasure clays or any mineral really. And the other thing to keep in mind that we don't have a pleasure clay standard, so we can't really compare your pleasure clays values with certified ones. All we can do is we can compare values we get with glasses, for instance. But that's what every other method is.
We're quite happy with the trace elements and silicates because we've recently got some confirmation that it is working well for unknown samples, and that actually comes from one of the MSc students, Kimberly, measuring trace elements in garnet, and then looking at the trace elements, particularly neodymium and samarium, using isotope dilution techniques, which give concentration, and the two numbers, the ppm level, matching almost identically between the laser and the ID solution. So that is comforting for us because we know that even for unknown samples measured and verified independently, we're getting good data.
I would also like to add that when I looked at novel applications, I made a personal selection. But there's many others. For instance, Ellen said we could try to do melt conclusions. What I did mention is we have 3 separate sulfide standards now. So in theory, we can embark on the sulfide in situ work, and it's just a matter of time and manpower. But in theory, we will be able to do it. We've got the standards. We've got actually 2 lasers. So we're thinking of using the existing UP laser to do sulfide work, because we're not quite sure how dirty sulfide work really is and how bad it can contaminate our instruments. But that's another thing that we're planning to do. But there's many other applications. I mean, there's, for instance, I have a student, Yash. He's doing appetite uranium net dating coupled with trace metals. That's another sort of emerging application. But there's many others. I just couldn't include all of them. But there's many.
One last question, perhaps, before we close it? Okay, well, thank you once again to John Hancock for the drinks and chips. And next week's Geotalk will be Ray Durheim talking about the recent ICDP drilling project into a fault zone, recently active fault zone in the Wits Basin. So please do join us for that. Thank you very much.